Three patients. So, cloud computing, the mysterious adventure that it is. An introduction to cloud computing. What is cloud computing? The canonical definition is an international standard that says cloud computing is a paradigm for enabling network access to a scalable and elastic pool of shareable physical or virtual resources with self-service provisioning and administration on demand. What does that mean? It means three really important things. I want to bring your focus to them. First, network access. So this is computing and networking capabilities that I can access remotely, even if I'm not necessarily logged into them locally or can't touch them. Second, scalable and elastic pool of shareable physical or virtual resources. What this part of the definition is telling me is that these are resources which can scale up or down depending on my demand. This is a box of capabilities from my perspective as the customer, a black box, which can get larger or smaller depending on how I want to use it. The fact that these are shareable resources means that I can distribute them between different teams in my environment, and I can share them between different customers if customers want to do that. Also, that at some level, usually several levels down, as we'll talk about, they're shared between customers. So if I'm thinking about one large high-performance computer, that might be a computer that can be accessed by multiple customers with those customer environments encrypted and separate from each other. And the third is self-service provisioning and administration on demand. All of this is able to take place in near real time as I'm spinning up and spinning down resources depending on how I want to use them. What do we mean when we say the cloud? The definition I gave you at the top of the presentation does a good job talking about some of the key ideas in what cloud is, but it's really important to understand that for all the diagrams of fluffy clouds on computer network spaces that you've seen, fundamentally the cloud is what you're seeing right here in these pictures. Large steel and concrete data centers filled with thousands and thousands of rows of server boxes. These pictures are intended not to give you an understanding of what all data centers look like. These are just a representative image, but it's important to try and convey the significance that the physical infrastructure behind cloud computing has in thinking about what the cloud actually is. So some key characteristics of cloud computing. First is that you need and are able to use network access to cloud services. Second, that you only pay for what you need from a measured service. So you take the computing capacity or the network capacity that you need for a particular moment, and then it expires when you're done with it. Third, multi-tenancy, that there are many customers working in the same space, working on the same set of equipment. Fourth, on-demand self-service to scalable resources. So we talked about with your ability to communicate with a resource and access it only as fast or as significantly as you need. Hold on one second. Presentation display issues. I'm going to work on these for a second, come right back. Try then is presenting this out of presentation mode. Can everybody confirm they're looking at the definition of cloud computing, or anybody who's able to comment? Yes, okay. President Michelle, Mick, you guys are great, thanks much. And can you guys also confirm you did not see or hear the last couple slides? Cool, heard them, no visual. All right, well, I won't walk them through you guys again on the audio track, but we'll just let you look at these for a second as we talk about the definition. So the slide here is the ISO definition I mentioned with those couple of key components about what cloud computing is. This slide, which has a lot of significance then, is the visual to give you some physical sense of what cloud computing actually is. And take a look at these. These are actually pictures of data centers in use today. Big acres-long buildings filled with these thousands and thousands of servers. Huge racks of power and redundant power systems, cooling infrastructure. The cloud, the significance of this is really that the cloud is a tremendously physical piece of infrastructure. Okay, and I think this is where we got caught up when you guys started paying me. A couple of key characteristics of cloud computing. The last one of this high bandwidth links to and between data centers. This is one of those issues that becomes more significant as the character of the computing service you're using changes. So as you are, or you or any customer are using services that are more data intensive or asking for more compute capacity from the actual cloud infrastructure, that bandwidth is going to become more and more important. This is just a couple of places. I give you an idea of the range of people and entities that are using cloud computing. Cloud computing started as something of a niche enterprise computing process where engineers and companies that did a lot of computing and networking work that were trying to create more efficient access to compute resources would change the way that they were buying, building, and selling those resources. At this point, it's become a default product for a lot of people that do work in computing. This is an example of one major cloud provider and the way that their infrastructure is distributed around the world. Data centers don't have to be located directly close to customers, right? Because these are services being leveraged over the internet, tens of millisecond lag time between customer and their service, which is what you'd get if you were crossing between, say, the East and the West Coast of the United States, isn't substantial. What this distribution is intended to do is to account for the variety of types of services that customers would want, and in some cases, concerns over the location of data. Although, as we'll get into, that's based on somewhat of a misunderstanding of the way cloud computing takes place. So, options for services and deployment. There's two ways to think about cloud computing once we've gotten past that physical analogy. First are the service models. Moving from top to bottom, well, left to right here as we see it, but top to bottom in the sophistication of the service, starts with infrastructure as a service. This is the most administratively intense way to consume cloud computing resources for you as a customer. This is where you have the most control, but with having the most control, you have to make the majority of decisions about how something is configured. In infrastructure as a service, the customer is given a piece of computing hardware, access to a server or a set of networking equipment or storage resources, and allowed to tie those together and run any kind of software they'd like on top of them. Infrastructure as a service is typified by something like a virtual machine, where customers get to run their own choice of operating system, as well as raw data storage, something like Databricks from a major cloud vendor. The next step up is platform as a service, or PaaS. Platform as a service is a little bit of a misnomer only because it's a huge category that encompasses a wide variety of different types of services. So the better way to talk about this is what distinguishes platform as a service from software as a service. The key distinction here is platform is giving customers the ability to plug into or use somewhat raw computing resources, not in terms of hardware, but in terms of software. I'll give you an example. A platform as a service example with machine translation would give the customer a point at which they could send data into a cloud service, have it translated and sent back out. That point, typically called an application programming interface, or API, would be a digital link for customers to be able to hook software into that service. So if I was building a mobile transport app and I wanted it to be able to translate things that users were asking into multiple languages, I could take that app as I had it written in whatever language I was using, point it at that application programming interface, and have user input translated into different languages. That's a good example of a platform as a service. Compared to that, software as a service, if you're writing in a word processor hosted on an internet browser and you are able to right-click a word and turn that into a different language, that's a better example of software as a service, where the software that you're being offered is refined and finished, intended for an end user to be able to manipulate in an easy-to-present way, typically through a browser, most typically through a browser. So infrastructure as a service is that raw hardware computing, virtual machines, my storage capacity. Platform as a service is that next step up in complexity, areas where companies like Amazon or Microsoft or Google are taking lots of intelligence, artificial intelligence offerings, services, and software and packaging that up and then distributing it to customers. And then software as a service, where I take something like a piece of software I'd see on my desktop and serve that over the internet, like a word processor or an email client. So that's service models. The other way to think about cloud is how cloud can actually be deployed. So if service models are how cloud is consumed, deployment models are how cloud is built and permissioned. All the way on the right-hand side, we see public cloud. In the middle is hybrid, on the left is private. There's a little bit of a distinction here that's important to understand. The size of the bubbles don't really accurately portray how significant the three deployment models are. Public cloud is by far the dominant way that people build and sell cloud computing capacity, especially in the United States. This is a set of infrastructure like the data center that we looked at, where any customer can use any type of resource and machine. Where customers are on the same machine, there's important security and cryptographic techniques that keep those users separated. but the actual public infrastructure associated with the public cloud is accessible to anyone. In a hybrid cloud, you have a public cloud with a company like an Amazon or a Microsoft, complemented by private computing infrastructure that's hosted by the customer itself. This is more typically seen with companies or enterprise environments that aren't necessarily comfortable with cloud yet, but want to sort of put a toe in the water. It's also more useful where there are specific needs on the customer side, for example, with companies that do business or operate in environments where they're not always going to have access to the internet, and so can retain some local computing capacity. Private clouds are like a public cloud, but limited to one customer. Now, advantages to that might be that you can control down to a fairly detailed degree what sort of things are in the cloud, how that cloud is run, and what sort of controls or requirements you want to apply onto that cloud. The downside to that, though, is typically tremendous cost. The reason public cloud is so popular and efficient is because it allows expensive computing infrastructure to be shared out to as many people as can maximally use it. So if I wanted to buy an expensive genomic compiler for my science lab, it was something I knew my graduate students were going to use 2 days out of every week, but it was something critically important for the project that we were working on. I might go and spend $1 million on that compiler. Taking the cloud model, I go to a company that's bought the compiler and I rent 2 days a week time to use that machine. That way I don't have to pay for the rest of the time it's being used. And the company that's bought it can sell that to other customers. Private cloud prevents that kind of efficient use of computing resources. Cloud service models. Let's talk a little bit more about IaaS, PaaS, and SaaS. So as we went through, infrastructure as a service is that raw computing layer. What you see here on the right-hand side are the 3 critical parts of any cloud computing platform: compute, storage, and networking. Something I need to think, something I need to store data that's been processed or will be processed, and networking to tie it all together. The virtualization fabric we'll talk a little bit more about later, but is essentially the computing technology equivalent of trying to tie all those resources together. There's some example products here down at the bottom. The distinction between IaaS, PaaS, and SaaS, again, is how consumers will actually use those services, what they're paying for, and how much responsibility they have for what's on that equipment. PaaS, similar to IaaS and SaaS, uses that metered pay-as-you-go access to services. Here, there's additional software and hardware that's being layered on top of those base 3 resources of compute, storage, and networking to be able to offer more complex services. A little bit less control if you're the customer, but also substantially more complex and capable services to have access to. And then last is SaaS, the sort of things that we're most familiar with when we talk about cloud computing, things like Office 365 or the Google applications. A couple of examples here of different companies and the services that they offer that fit at each of these different levels. Amazon EC2 or VMware's vCloud are good examples of an IaaS service. Google's App Engine or Windows Azure, really good example of a platform as a service. And then software as a service, like we talked about, Google Apps or Microsoft Office 365. Talk a little bit about deployment models just for a second. Here we have this idea of the private cloud, right? We talked a little bit about what that exclusive control by a single customer might look like. 3 other examples in thinking about what various versions of a public cloud might look like. On the left-hand side of that right box is the commercial public cloud. That is the bulk of how cloud is consumed and built. Regional cloud is where a public cloud might be limited not to a single customer, but to customers in a single region, a single part of the world. And then a country cloud limits that a little bit more specifically to a single country. The downsides to that regional and country limitation is twofold. First, it limits what companies are able to offer. Typically, when a company rolls out a new service, like say an advanced machine learning powered translation mechanism, it's going to make it available to as many customers as possible in the public cloud. On the other hand, if a regional cloud has set up special controls, it might be hard or impossible for that company to roll out a product from the public cloud directly into that regional cloud without making a special effort. When you narrow that down to a country cloud, that same problem emerges. And so this potential pool of users that are going to use that service to make it efficiently available to all shrinks even further. So these different deployment models have some potential utility, but also some potential drawbacks. So it's useful to think about those in context. Now we're going to move a little bit into the actual foundational technology associated with cloud computing, section we call building a cloud. So we've talked about IaaS, PaaS, and SaaS. The reason I bring these back up is to show you the next chart, which we talked a little bit about responsibility, but this is the critical takeaway for these different consumption models. So what are you looking at? On the left-hand side, under the responsibility column, moving from data classification and accountability down to physical security, are some different key security processes that you have to consider with any computing environment. Moving from left to right on the top in the x-axis are the different types of computing deployment model you might look at, from on-premises through IaaS to PaaS and ending with SaaS. The two colors denote the different responsibilities between customers and the cloud service provider. Blue is the customer, while gray is the cloud service provider. What this chart is intending to show is the distribution of responsibility at these different deployment models across the different security processes. So, for example, if you're a customer running your own computing equipment on premises, you have responsibility for every part of the security chain, from physical security to data classification and accountability. If you're consuming platform as a service, cloud service provider has the responsibility to make sure that the infrastructure that you're using is physically secure, isolated from attack, theft, or any kind of criminal activity. They also have the responsibility completely to make sure that the host infrastructure and the networking gear that it's being used over actually is secure and adheres to a relatively coherent set of security controls. I mentioned at the top that ISO standard that define cloud computing. There are similar international standards that define how best to secure computing, storage, and network equipment. Those are the kinds of standards that a large cloud vendor would want to follow. A quick note here, those kinds of controls can be difficult to apply if countries or regions have set up specific local standards that maybe don't meet those standards for their own cloud services, which is one of the downsides to that regional or country-specific cloud deployment. Application level controls and identity and access management under that platform as a service column, those are cross-shaded. So you can see that responsibility is shared between the cloud provider and the customer. For something at like an application level control, if I go back to my machine translation example, the cloud provider is responsible for making sure that the operating system that's running that machine translation service on its own infrastructure is designed and implemented in a relatively secure fashion. If you're the customer, on the other hand, you have the responsibility over who, for example, has permission to access that service and the user data that goes into and out of it. So there's that shared responsibility. Some parts of that lie with the consumer and some parts of those lie with the provider. As you go up the chain from on-premises to infrastructure to platform and then later software as a service, more and more responsibility for the security process goes to the cloud provider. This can be advantageous where cloud providers are able to take lessons learned from tens of thousands or hundreds of thousands of customers and apply them across their entire infrastructure. It also means that in some cases, customers may have slightly less visibility or control over the security processes being used for their equipment. So it's something important to consider when you're thinking about different levels of cloud service. So quickly, you want to walk through what exactly sits underneath this cloud computing technology. So we're going to talk a little bit about the fundamentals behind what makes cloud possible. The three sort of frames that I want to use for this part of the presentation, so ways to think about organizing these ideas, are talking about basic pieces of technology, how those are spun up together into an architecture that supports the operation of cloud. And then for each section, we'll talk briefly about the risks and benefits policymakers should consider. This is the technology of the cloud abstracted into a useful model. Starting at the bottom with data centers, moving up to software-defined networking, through the hypervisor, which is a critical enabler of infrastructure as a service, through container managers, which are enablers of platform as a service, and into broadband, which has helped make software as a service popular and possible. Starting with data centers, the foundation of the cloud. We go back to that picture we've seen, these large buildings of steel and concrete and aluminum spaced out far away from large population centers in relatively secure parts of the world. These are the heart of the cloud, the actual physical infrastructure that keeps things running. The obsessive part about running a data center is maximizing power and heat efficiency. All of that heat comes from all of that power being pumped into these little rows of servers, tens of thousands depending on the size of the facility. Each of these servers can be focused on different parts of those core resources we talked about, computing, storage, or networking. They'll have different specialized compute or networking infrastructure depending on their purpose, and they'll usually be arrayed in racks of 20 or 30, aligned with other servers with a shared purpose. The operation of all these different pieces of infrastructure together creates that management challenge I talked about earlier with power and cooling. This gives you a quick example of how data centers and their power and heat efficiency have evolved over a series of generational developments for a major cloud provider. Starting in generation 1 in the early days, you have that measure 2.0 PUE. power usage efficiency. As you can see, going over time, that PUE number has gone down substantially. As you think about operating tens of thousands of servers in a large facility, the power usage of even a small change can start to be a dramatic improvement to not only thermal efficiency, less power means less heat, but also cost. Less power is less money. So this becomes a major focus for how cloud infrastructure providers are able to build and provide their services. Why is this important for our discussion? The really critical takeaway: economies of scale matter. The larger these facilities and the more extensive the facilities on offer from a particular provider, the better a chance they have to learn how to efficiently offer these services. That means reduced cost to the consumer and potentially more effective and resilient infrastructure for that use. A couple of key risks and policy considerations to think about. We've coded these with easy happy and unhappy faces for you just to cue into some of the key ideas involved. Where data centers are located is typically much less of an issue of where customers are and more about efficient delivery of services based on the way a company has architected its service. Strong requirements to place data centers in particular locations or changing security controls away from international standards can make it difficult to deliver cloud services of the same kind delivered to the rest of the world or even at all to a particular region. One of the key risk considerations for placing a data center is the potential risk of a natural disaster or other mistake or intentional form of harm that could create damage to the facility or disruption. Big obsession for people building these kinds of facilities is access to power and cooling. Without power and cooling, you have a lot of very warm boxes that aren't running. At the end of the day, that's not very good if you want to be delivering cloud services. Thinking about the architecture of these cloud services, usually effective security programs associated with a cloud facility are going to have strict controls on how people get in, what they can do, and where they can go. Just walking up to a server it's difficult to know it's impossible really to know what's being run on it or trying to manipulate it. These controls are in place to make sure that people don't steal servers, take them home, sell them, try to go through random customers' data, sell it. That kind of physical infrastructure security is a really important part of the cloud. It's another one of those reasons to really think about and focus on the physical side of what cloud computing is. And lastly, in operation, with the way that cloud computing is scaled out, again, if you're running those tens to hundreds of thousands, even millions of servers across the world, you start to see a lot of different kinds of attacks and a lot of different kinds of security challenges. Large cloud computing companies are able to take those lessons and leverage them across a wide range of customers. Where regulations are in place to potentially prevent that kind of information sharing across borders, it can be difficult to use that efficiency of scale to protect people. So now let's move into networking and talk about software-defined networking in terms of wiring the cloud. Software-defined networking is not a new phenomenon, but it is relatively recent in the context of the history of computing. Software-defined networking, simply put, takes the traditional networking model, which you see here on the left-hand side, where individual flows of data and the direction of where that data is supposed to go live together on the same machine. So if you think about your home router, if you want to access the internet, you're talking to the router, and the router is taking the packets of your data, which you're trying to go to google.com or espn.com, and directing those to different places on the internet. Software-defined networking separates that data and control plane so that you can take a device and have it moving data from different machines without the intelligence to actually know where that data is supposed to go. Instead, the intelligence comes from this centralized controller machine. This allows for more efficient and in some cases more secure transfer of data between different pieces of infrastructure. Software-defined networking also makes it possible to build new network architectures that are more efficient and, in many cases, less power hungry than when all this intelligence was combined on every device, even though it wasn't usually needed on every machine. That network layout becomes really important as we think about the way cloud has evolved in the last few years. So a quick example of the kind of thing I'm talking about when I talk about network architecture. On the left-hand side, you have a first-generation network, an early cloud offering. On the right-hand side, it says generation 3, but it's actually a fourth or fifth iteration of a different network architecture with the same cloud service provider. What's the difference between these? Well, you can start to see that the density of connections here at the bottom are typically very vertical, right? And they're concentrated at this lower level, and there's very few connections at the top level. Here on the more recent version, right, we have tremendous density of connections, many more of these little links between machines. And they're also incredibly dense even as you go up higher into this network. Why does this matter? The way cloud computing has evolved, it typically started being offered from companies that offered services over the internet, where the primary path of communication was between the customer, somewhere out here, and the computer or the server that they were communicating with, somewhere in the network of the provider. Thus, most of the communication between customer and service was what's called north-south, moving into and out of a data center. Cloud computing typically allows for users to leverage resources that have been combined across many different pieces of infrastructure or even in different data centers. For example, in that machine learning example we talked about for platform as a service, the data that you send into that service is going to get stored, sent to something to process it, potentially sent to a second machine to validate or error check, and then sent back out to the consumer. There are multiple different stages and different types of resources that can be used at each of those stages. What that means is that instead of a piece of data just coming in once, hitting a server and bouncing back out, instead now you have a flurry of connections between different resources within a single data center to offer that one, in this case, platform as a service as an example. That kind of networking, which is moving laterally between resources, is better known as east to west networking, characterizing it differently from the north to south of these first generation networks. SDN allows that kind of network layout to be changed much more rapidly, because you no longer have to sit and plug and re-plug in wires between different machines just to change the path of data flow between them. That networking, that physical networking and changing of wires still matters, but major network architecture changes like this can be done much more easily. And then we talk about operation. Using SDN within the context of this kind of newer network, it allows cloud service providers to do things like shape the size and the composition of a network to meet customer demand. Previously, I might have sold, as a cloud service provider, I might have provided resources to a customer and had them make the choice about where and when those resources were turned off and turned on. And if I didn't want to access a part of a network, I had to turn it off to prevent it from being accessed. Now I can literally, on the fly as a cloud service provider, disable access to part of a network by changing the configuration, changing the layout of the entire network. That allows cloud service providers to do things like set really strong security boundaries. If I have two computers, computer A and computer B, and I want them to talk certain times of the day because my business is open and operating and I want those two to be communicating, I can make sure that they're wired up as part of a network. At some point when my business closes and I don't want computer A and computer B talking, I can literally disconnect them, preventing people from moving data between them. That kind of flexibility and security is the hallmark of what software-defined networking brings to the cloud computing environment. A couple of risks and policy considerations. First, requirements for particular kinds of computing equipment or services might make it difficult for cloud providers to operate in the way that they're designed to. Most cloud providers operate with what's called a design once, build many times model, where they build their cloud service architecture and try to deliver that around the world. When individual portions of that world start requiring particular changes that don't fit with the way a design is accorded, it may be possible for the cloud service provider to meet those requirements, but it may also increase costs and reduce the sort of services that are available. Talking about architecture, the biggest difference between early cloud services and today is that move from north to south, customer to server, to east to west, between servers kind of traffic. And then in operation, many ways that people think about how they regulate security and computing today were built on enterprise computing models from the 1980s and 90s. The way networks were laid out, the way computers talk to each other, and where there were opportunities to do things like, for example, build a firewall. Today, with the way computing is laid out in cloud computing, it's easy to break those regulations and old assumptions because companies are changing the way those technologies are deployed on a regular basis. So with the example of a firewall, in the old days, it may have been good for security to say, I want to know exactly what's coming in and out of a network. And so I'm going to assume a hard security boundary between customer on the outside and my servers on the inside. Today, with the amount of communication taking place between servers, that boundary no longer exists. So it's not enough to simply put a firewall between the outside and the inside. You now have to be incredibly aware of what's going on within a network. Older regulations might not take that into account, and so may miss opportunities to better secure users. Moving up this stack, we talk about hypervisors and enabling infrastructure as a service. A hypervisor is a piece of technology that allows for something called logical isolation of data within a single server. Logical isolation is basically a digital technique to keep two customers in a single machine separated. It involves a series of cryptographic and software protocols to prevent user A from seeing user B's data or access to computing resources like the processor or stored memory. A hypervisor is what sits at the foundation of the ability to offer infrastructure as a service, taking one computer and using it across many customers. Here we have a quick visualization of what those multiple clusters might look like. The hypervisor sits on top of this technology called virtualization, which allows the resources of a single computer to be taken and shared out between multiple users. Going back to that definition of what cloud computing is, shared resources is absolutely the foundation. Multiple users sitting on a single computer is something called multi-tenancy. It's that multi-tenancy which sits at the root of cloud computing's ability to be efficient and cost-effective. Looking at operation of these hypervisors and the way that virtualization is actually implemented, the key that we see here is elasticity and decoupling. Resource elasticity is the ability for customers to access and deliver different resources depending on their need and depending on the time and what's available. Resource elasticity from a hypervisor allows for users to be shunted between resources depending on the demand of those different computers. Decoupling hardware and software means that hardware and software no longer have to sit on the same update cycle. So imagine when you buy a laptop. Nowadays, you're able to update operating systems over the web. But as for larger and more complex computing systems, software isn't always updated at the same time as hardware. So it can be difficult to sync those up and have equipment and software that talk to each other. On the cloud, because those are entirely separated, I can update and change software as frequently as I like, whereas the computing infrastructure can change when it's most cost effective. Looking again at that security responsibilities chart, we see in infrastructure as a service, the cloud customer bears more responsibility than in any other cloud service model. So the cloud provider mostly has control over physical security, also has some responsibility for host infrastructure and network controls. And then thinking a little bit about risks and policy considerations, the way that we've talked about scale and cloud computing before, cloud service providers' ability to manage tens of hundreds and even thousands of millions of servers puts them in an opportunity to see attacks and security holes and flaws targeting customers across a variety of different environments, giving them tremendous insight into the way attackers function. Thinking about architecture, one of the challenges in regulating the way cloud focuses and is secured is concerned with how the cloud is actually built and deployed on a regular basis. Regulations that think about computing as an old enterprise model in the 1980s or 90s, where large computer systems were built and delivered to a single customer over a period of years, might not be able to keep up with the way cloud is built today. And then thinking about operation, a couple of the points we've already hit. Access to the public cloud gives customers access to the most cost-efficient services on the planet. Private clouds, whether linked to a particular region or country, can limit access like that. Moving a little farther up the stack to container managers and microservices, talk a little bit about platform as a service. A microservice is a piece of software that's been fragmented into its most critical parts, and those parts allowed to run independently. Why does that matter? Thinking about and going back to our metered access idea in cloud computing. If I want to run a web server that talks to a database, but the majority of the work being done by that web server and database is done by the web server, it can be cost inefficient to run them both at the same capacity if the majority of the work is done by the web server. Microservices allows me to split those two up and run them only as much as I use them. It is in some ways an extension of the basic cloud model, a little bit farther down the way software is built. So I no longer need to think about software as one big monolithic piece, but can actually break it up into its component parts. The way that turns into an architecture is that microservices are tied together to create these processes like platform as a service, thinking about things like that machine translation, allowing cloud services and service providers to update that service at different components and different points, depending on the need, depending on when new software becomes available, rather than waiting to update everything all at once. Containers are a way to deploy those microservices more efficiently and more rapidly than using a traditional operating system or what's called a virtual machine in this context. Containers are small, digitally isolated software packages that can be run from what's called a container manager placed on top of a traditional operating system. This allows cloud providers to update software much more rapidly. Thinking about the operations of these microservices under a category of what's traditionally called serverless computing, customers no longer have to think about the administrative overhead associated with turning on a computer, installing an operating system, and having to pay for all of the different operations they do on that operating system. Now, cloud providers can actually combine single uses of a particular service, like that web server we talked about, into what's called a request unit. That allows for maximum efficiency and minimum administrative overhead to the user. Thinking about that security responsibilities chart, which you've probably seen now a few times, as you move farther up from infrastructure to platform and then last software as a service, more and more of the security responsibility for those operations are being taken on by the cloud provider. This means less administrative overhead for the user and additional security expertise from the cloud provider being leveraged for the customer. A couple of risks and policy considerations. Microservices, because they're relatively new, not necessarily new in terms of innovation, but new in terms of broad use, way of deploying software to customers, they may not necessarily be considered under existing data classification and regulatory regimes. Second, in thinking about the architecture of the way these microservices talk to each other, containers, which are those little digital entities we talked about that allow microservices to be deployed, can, in many cases, contain the same sorts of security flaws and vulnerabilities as a regular piece of software, which means that developers and customers need to be considerate of the way that those containers are developed, that they're developed securely. And then in thinking about the operation of these microservices and serverless computing, when the public cloud is fragmented into lots of small national or regional clouds, the delivery of those microservices may not have the same gains in efficiency as they would if they were accessible through the public cloud. Lastly, looking at broadband and how it enables software as a service. Broadband allows users to access tremendous amounts of data over the internet at relatively high speeds. That becomes incredibly important when the kind of data being moved and the processes being transferred from a single computer, a local machine, for example, to a cloud resource grows substantially. The other side of broadband computing, in addition to bandwidth and the ability to move large amounts of data, is standardized web protocols, where a cloud provider can use a commonly used browser, one of several, that supports the same kind of standards and protocols in Africa or in Europe as it does in the US or Asia. Hold on one second. Unfortunately. We'll finish up the presentation here. Ruby on Rails, REST, and JavaScript are an example of three common web protocols that have been instrumental in the spread of software as a service computing across the internet. Ruby on Rails and JavaScript provide a common development foundation for people to build apps that can then be run through software as a service providers, whereas REST is a standard for what's called the application programming interface for allow for common ways for people to access different kinds of data. All of that comes into and becomes important when you think about access to technology and technology gains, especially in the developing world, where the ability to write an application that can be hosted on a major cloud provider like Windows Azure or Google App Engine or Amazon EC2 is enabled by building applications in the context of these standardized protocols. Last, thinking about how all of those different technologies and that architecture turns into operation, we get to what's called development operations or DevOps. DevOps is a new way of building and deploying software that emphasizes lifecycle configuration management and testing, where instead of building a single piece of software and then distributing it to the user or distributing it to another part of the company for testing and integration and moving through that process in a waterfall motion, DevOps actually allows for the development, testing, security, deployment, and integration process to be put all into one bubble and run simultaneously, or at least very closely tied to each other. This makes for more rapid deployments of new software and more secure development of code. Looking again at that security responsibilities chart, is at the end, we have software as a service, which takes a look at the way that responsibility is distributed between customers and cloud providers. Where there's opportunities for customers to control security of their data, that data classification and accountability piece remains the most important part of the relationship between customers and their security of their data. That data classification responsibility is never something that can be moved to the cloud provider. So it's important to understand when you use a cloud service that how data is categorized and who is supposed to have access to it will always remain the responsibility of the customer. Thinking about a few risks and policy considerations here, access to this kind of technology, especially broadband and use of these standard protocols in development, can help capture the economic gains associated with cloud computing. The architecture associated with software as a service relies on these commonly used web frameworks, and so it emphasizes the importance for rapid and effective vulnerability disclosure. It can be difficult for software to be run and maintained securely over a long lifespan if people find vulnerabilities in it and never disclose them to the company running that service. In countries that make vulnerability discovery and disclosure illegal, it makes it less likely that individuals are going to find and disclose those kinds of vulnerabilities, thus making them the software that they're involved in less secure. And then looking at development operations or DevOps, Rapid changes to software fit with the way cloud services are being delivered efficiently and securely to customers today, but it may not necessarily fit with the way regulations have been designed to think about computing in the past. So thanks all for sitting through the presentation. I look forward to a couple of questions. Just as a heads up, the next Tech Accord webinar is going to be December 17th, 2018. It's going to be talking about protecting your hardware. And so with that, I can see a couple people in the chat window. So if anybody's got questions, go ahead and ask. The next boom regarding cloud computing. And if I'm interpreting boom correctly, you mean the next big technological leap? So the next big technological leap in the way we use cloud computing is probably going to come from those microservices that I talked about. Right now, the way that those are developed, they're typically used by the cloud service providers themselves to deliver platform as a service and software as a service to customers. The next big jump is going to be when large institutions that build software themselves, companies like SAS, General Motors actually is a great example, Adobe, start to integrate those kinds of microservices into the way that they develop software. So you actually start to see software as a service or software available over the internet as the default rather than an option with the way many of these companies are building products. The implication for that is that cloud service providers are going to have to build infrastructure not differently, but in a more extensive and accessible fashion for all those different kinds of microservices. But also means there'll be a lot more attention on the security of those containers and the container managers I talked about. Okay, from Mick. Absolutely. From a risk perspective, do you see an increasing insurance as an option given the inability to shift accountability? Most large providers have standard terms and provide little flexibility or focusing on cloud eligibility. It's a great question, Mick. And cyber insurance is an interesting part of the security landscape when we think about cloud computing. Three answers to your question. First, I think that insurers are starting to get their hands around cloud computing. One of the problems that's held cyber insurance back, obviously it's a large and growing market, but it's substantially smaller than it might be. One of the reasons for that is that many insurers struggle to understand the intricacies of risk assessment for these kinds of computing platforms. It's not because insurers are not smart or not working hard on it, but it tends to be that the kind of expertise associated with understanding the risk profile from an information security standpoint of one of these large pieces of infrastructure comes from having worked on them or being in that industry. And this is not an area many insurers have worked on or in. So I think that's part of the challenge is as insurers get to know their customers and these technologies more effectively, they're able to write better and more detailed policies. The second answer to your question is associated with those large providers. One of the challenges that we run into when we think about cloud computing is actually understand who's being covered when you think about a policy. If I'm the customer for a software as a service, the thing being insured might be my business operations. So guaranteeing that if anything were to go wrong and I'm no longer able to sell my services, I have some insurance policy for the money that I'd otherwise be bringing in. That's usually called business continuity insurance. In other cases, when we're talking about platform or infrastructure as a service, the thing being insured may actually be the computing infrastructure. And there, companies aren't necessarily as quick or as excited to insure large pieces of physical infrastructure and equipment that they can't necessarily have good access to. So one of the things to think about as these policy evolves is trying to understand exactly who's being covered. There are insurance policies available for large cloud service providers. They look very different from the policy that a small company might get. And third, thinking about cloud eligibility and these flexibility. This is another area where I think cyber insurance is just going to have to mature and evolve. Because of that misunderstanding or lack of really accurate understanding around the risk of cyber events I talked about earlier, many insurers actually limit coverage by writing very specific and narrowly tailored policies. That can make it difficult to obtain coverage for broad or hard to specify harms, which isn't necessarily a bad thing. But as insurers start to understand risk profiles of their customers and different types of companies better, that likely will change. They no longer have to actually mitigate their risk by writing these very specific policies. Any other questions? Question on auditability. Auditability of what? Question. So talking about cloud service providers, there are a range of standards, international and in some cases national, as you mentioned, Sarbanes-Oxley as an example, of compliance and security regulations that apply to cloud service providers, which you can do if you want. This may be something where we can send some links around, but they're pretty easy to find if you Google online. The major US cloud providers like Microsoft, Amazon, Google, even IBM and Oracle will have their regulatory compliance documents posted somewhere online on their company websites. And so you can actually walk through these very detailed assessments that are done for things like SOX, but also a handful of other major security regulatory requirement bodies. So I think from an auditability question, we're actually seeing a lot of that already. Cloud computing services are used by people in the financial sector, from major investment banks to small commercial outlets, to even local retail bank facilities. So I think auditability, or the ability to audit machines and data being used by a financial institution in a cloud service provider, in some cases, in many cases, already exists. Where it doesn't, it might be based on client-specific security regulations or particular practices within a niche financial sector. Questions? All right, not seeing any. Thanks everybody for coming to the inaugural Tech Accord webinar. I hope you all enjoy the rest of your day, and thanks for watching.